Captain Nikolai Essen of the Imperial Russian Navy faces a brutal binary. His fleet is trapped, his anchorage is compromised, and the enemy is closing in on all sides. He can surrender his 11,000-ton pre-dreadnought battleship to the encroaching Japanese forces, allowing them to repair and turn the weapon against his own nation. Or he can execute a precise sequence of technical sabotage to guarantee the vessel will never fly a foreign flag. It is early 1905 at Port Arthur, and the Russian Pacific Fleet has been systematically decimated by relentless plunging fire. The rest of his squadron is already resting on the bottom of the shallow inner harbor. Essen refuses to join them. With Sevastopol crippled and barely able to move, Essen uses what steam he can, and tug assistance where needed, to get the battleship out of the confined inner basin and into deeper water beyond the harbor mouth. He navigates toward a steep underwater drop-off. Once in position, he begins a deliberate, uneven scuttling. Damage arranged to make later recovery far harder than a clean, upright sink. When a ship sustains symmetric damage or opens its lower valves evenly, it settles upright on the sea floor. An upright hull, especially in shallow water, preserves its core structural geometry and presents a relatively straightforward recovery profile for heavy salvage operations. To permanently deny the vessel to enemy salvage engineers, Essen must eliminate that geometry. He orders his crew to abandon ship, as leaving only a skeleton team to open the seacocks and flooding valves on exactly one side of the lower hull. This deliberate, uneven water ingress initiates a catastrophic chain reaction. It instantly destroys the transverse stability of the warship. As thousands of tons of heavy seawater rush into the starboard compartments while the port side compartments remain completely sealed and full of buoyant air, the internal equilibrium is shattered. The center of gravity shifts violently outward, pulling the ship off its vertical axis. The immense weight of the incoming water drags the starboard rail under the surface, causing the ship to roll sharply onto its beam ends. The warship heels hard to starboard, rolls deeper, and quietly founders beneath the surface. The battleship Sevastopol goes down in roughly 180 feet of water, about 30 fathoms, settling with a heavy list rather than upright in the shallow mud of the inner harbor. At that depth, the barrier is not some instant crushing force. It is access, time, weather, and the sheer difficulty of working a massive wreck outside the protected basin. In 1905, that depth and position make salvage effectively prohibitive. Possible to imagine on paper, but ruinously difficult in practice during an active siege and in exposed water. Essen gets his denial. Sevastopol will not be a captured weapon. But inside the inner basin, the rest of the squadron has no room for Essen's trick. The water is too shallow to let a battleship roll over and lock itself into an unrecoverable shape. So when the Japanese guns finally break their backs, the ironclads can only do one thing: sink straight down. They settle into the soft harbor floor with little room to roll, some nearly upright, others locked in a stubborn list. Enough of each ship still shows above the surface to mark the grave, but not enough to make recovery simple. For the victorious Japanese commanders, the sight is triumph with an invoice attached. They have captured a fleet, but it sits flooded, battered, and half-buried where it fell. Salvage teams are dispatched at once, and what they inherit is not a simple lift, but months of winter engineering in a harbor that refuses to give up its dead. And the reason these ships went down the way they did is baked into the way they were built. A pre-dreadnought battleship is essentially a floating fortress, optimized for a very specific type of mathematical engagement. Naval architects of the era designed these massive vessels to survive flat trajectory gunnery duels on the open ocean. Because enemy shells were expected to strike parallel to the water, the maximum thickness of protective steel was concentrated entirely along the vertical waterline belt. The sides of the ship were impenetrable walls of hardened armor, engineered to defeat direct kinetic impacts. However, this heavy fortification came with a strict weight penalty. To keep the warships buoyant and stable, the horizontal surfaces spanning the top of the vessel were left dangerously thin. This structural compromise created a severe geometric vulnerability. When the Japanese Third Army finally seized 203-meter hill on December 5, 1904, they gained direct overlook of the Port Arthur anchorage. From that height, they hauled up 28-centimeter siege howitzers, the 11-inch weight of the siege. and began dropping shells onto the fleet at a steep, top-down angle, right where pre-dreadnought protection was thinnest. When these massive projectiles impacted the fleet, they met far less armor than the thick belt at the waterline. The thin, horizontal deck armor was shattered by repeated hits from above. Some shells punched through multiple layers before bursting, others tore up the upper structures, started fires, or were later found unexploded. The effect was the same: chaos in the spaces that kept a ship alive. Under that pressure, with surrender looming and the harbor becoming an aiming range, Russian crews opened Kingston valves and scuttling fittings to sink ships lower and reduce the target they presented. In the inner harbor, the sink is not a fall, it is a stop. The damaged ships hit bottom before they can fully roll, and the mud grips their keels hard enough to hold them close to level. Water swallows the lower hulls and primary decks, while turrets and towers remain above the surface, turning the anchorage into a line of half-submerged fortresses. The Japanese had successfully neutralized the Russian Pacific Fleet without engaging them in a traditional naval battle. By exploiting the geometric flaw of horizontal deck armor, they turned the anchorage into a steel graveyard. The howitzers had done their work, but they had done it in a way that left every hull a different, jagged problem, and Salvage would have to solve them one by one. The plunging fire did not just poke clean holes through the warships, it caused catastrophic, multi-level structural collapse. The decks were peeled back like tin, leaving gaping, jagged craters that exposed the deepest internal compartments directly to the sea. The sheer size of the 11-inch entry wounds and the internal blast cavities meant that vast sections of the vessels were now entirely open to the surrounding environment. The water pouring into those open wounds is not clean sea. Port Arthur's bottom is heavy silt, and the blasted openings begin to drink it in with every tide. The ships are not just flooding, they are swallowing the harbor itself. The Imperial Japanese Navy does not wait for peacetime or spring thaws to claim its prizes. Before the surrender even settles into routine, engineers are in the captured anchorage, because the war is still burning and every hull matters. They step onto ice-choked docks and into near-freezing water, where a diver's working time is measured in brutal minutes. To raise a ship, engineers must restore its internal buoyancy by displacing the flooded water with air. Air cannot displace water if the hull is riddled with artillery craters and ruptured bulkheads. The hull must first be made mechanically continuous. Japanese divers descend into the freezing, pitch-black water to map the exact dimensions of the catastrophic damage. They find torn steel plates peeled outward and massive internal cavities. The divers must navigate twisted metal and submerged debris fields without any visual reference. Every movement is a calculated risk against torn bulkheads that could easily snag an air hose or trap a man deep inside the flooded wreckage. For smaller ruptured seams, divers carry down cement bags, quick-setting patch compounds, and timber and plate stops. In black water, where sight is useless, they work by fingertips, finding the leak, bracing it, and choking it off, until the hull's smaller bleeds finally slow. Concrete is entirely useless against massive structural voids where explosions and collapse opened whole sections of the ship. To bridge those gaps, Japanese engineers use external caissons and cofferdams, immense timber and plate boxes built topside to match jagged openings, then lowered and bolted over the breaches. Once a caisson is seated and sealed, pumps can lower the water inside that box, giving divers a controlled pocket to work against the hull. It is not open air at depth. It is a sealed workspace, sometimes assisted by compressed air methods, created so repairs can be fitted, drilled, bolted, and made tight enough for the next step. Shielded as much as the caisson allows from the freezing harbor, they drill, bolt, rivet, shore, and plate over the primary damage, forcing torn steel back into something continuous. It is slow, methodical, and brutally dangerous. If a seal slips or a timber frame shifts, the sea will hammer back into the workspace in an instant, turning the repair pocket into a trap. The teams operate continuously, driven by the urgency of an active wartime timetable. The Japanese salvage teams construct and sink these massive timber shields across the harbor. Inch by inch, they close the fatal wounds on the pre-dreadnought battleships and armored cruisers. They replace the torn horizontal decks with bolted steel and heavy timber plating, reestablishing the watertight integrity of the upper boundaries. The sheer scale of this combat engineering phase pushes the limits of winter salvage operations. Men are constantly rotated out of the freezing water, fighting exhaustion, hypothermia, and the relentless pressure of a ticking strategic clock. Slowly, the engineering teams seal off the sea, transforming the shattered wrecks back into enclosed, albeit flooded, vessels. The outer steel shell is finally intact. The immediate threat of the ocean pouring back into the ships is neutralized. Achieving a watertight boundary only solves the exterior equation. The salvage engineers prepare to pump the internal water out of the sealed hulls, expecting the massive vessels to slowly regain buoyancy and break free from the seabed. They quickly realize the harbor floor has completely altered the internal mass of the wrecks. The timber cofferdams successfully hold back the sea, but the interior compartments are packed with a heavier, more stubborn enemy. Inside the lower hull of a sunken battleship, there is no light, and a diver possesses zero visibility. A man descends into the flooded magazine, and his hands immediately sink into a dense, freezing matrix. His touch sensors are entirely overwhelmed by a thick paste that fills the space from the deck plates to the overhead steel beams. He is completely blind. It's suspended in pitch-black water, trying to navigate a maze of torn bulkheads that is entirely packed with solidifying harbor mud. The Japanese engineering teams quickly realize that the ocean water is not their primary adversary. It is the heavy, viscous marine silt that has flowed through the blast craters and settled deep into the bowels of the Russian fleet. Because the cofferdam sealing successfully isolated the inner hull from the open sea, the engineers initially assume that evacuating the trapped liquid will restore the required buoyancy. They run standard salvage hoses down into the dark compartments and engage the steam-driven surface engines. The machinery quickly chokes and violently seizes. Standard lift equipment is designed to move thin, fluid seawater. It cannot process the dense, heavy sludge that now coats every internal surface of the warship. That sludge becomes ballast, dead weight that locks the flat-bottomed hulls to the harbor floor. To break this deadlock, the Japanese deploy massive, heavy-duty centrifugal pumps. This requires executing a process known as mud suction. Instead of relying on simple vacuum displacement, a centrifugal pump uses a high-speed rotating impeller to create a powerful internal vortex. This spinning vortex generates an immense, continuous pull, capable of lifting high-density particulate matter alongside the water. It essentially functions as an industrial vacuum designed to violently agitate the solid harbor mud, mix it back into a fluid slurry, and force the thick mixture up through the reinforced discharge pipes. The engineers lower the heavy intake hoses deep into the black compartments, guiding them by feel directly into the thickest concentrations of sludge. Operating these massive machines is a relentless, brutal grind. The pumps run continuously day and night, vomiting thick black slurry out into the surrounding bay. The machinery frequently clogs with jagged shrapnel, splintered wood, and ruined equipment pulled from the flooded compartments. Every blockage forces the blind divers back down into the freezing darkness to manually clear the intake grates. Working by touch, the divers pull jagged debris from the heavy suction nozzles, risking their hands in the freezing water to keep the industrial vortex spinning. The operation stretches on for months of uninterrupted industrial labor. Day after day, crews fight cold, abrasive mud, and mechanical failure, clearing the ships one blind compartment at a time. The volume they pull out of the lower decks is staggering, and keeping the steam plants fed becomes a logistics battle of its own. Slowly, the mechanical advantage shifts. As the immense volume of internal mud is discharged into the harbor, the dead weight pinning the ships downward steadily decreases. The lower compartments finally fill with buoyant air. The physics of the harbor floor begin to change. The thick sludge surrounding the exterior of the keels slowly loses its gripping power. With a sudden, violent shudder, the immense steel hulls break the suction of the seabed. The pre-dreadnought battleships and armored cruisers rise from the mud, breaking the surface of the inner harbor. The dead ironclads are afloat once again. The surface crews quickly secure the massive steel beasts, tying off heavy mooring lines to stabilize the newly floating wrecks. The harbor is conquered, and the captured vessels have been forcibly resurrected from the silt. The exterior structural patching holds back the sea, and the centrifugal pumps continue to manage the internal water levels. Extracting the mud restores buoyancy, but raising a dead ironclad from the harbor floor is only the first half of the equation. The engineering calculus fundamentally changes the moment a dead ship breaks the surface. For months, the primary objective was purely vertical, focusing entirely on breaking the static grip of the harbor bottom and restoring basic buoyancy. Now, the Japanese Naval Command faces a completely different mechanical reality. A floating wreck is not a seaworthy vessel. It is a highly unstable mass of torn steel and temporary timber patches, completely lacking its own propulsion. The strategic mandate requires these prizes to be integrated into the Imperial Japanese Navy, which means they must cross hundreds of miles of open ocean to reach the naval arsenals in the home islands. The decision flips from localized structural isolation to dynamic, open water transit. Every mile of open ocean multiplies the dynamic stress on the salvaged hulls. The temporary repairs engineered in the freezing harbor were designed to withstand static water pressure in a sheltered anchorage. They were never meant to absorb the violent pitching and rolling of the open sea. Wave action threatens to flex the heavy steel framework, potentially snapping the rigid timber seals and shearing off the bolted plates. If a single major patch fails during the tow, the massive warship will rapidly flood and sink in deep water, permanently losing the prize that cost months of brutal winter labor. To mitigate this critical vulnerability, naval architects have to calculate towing stresses for crippled pre-dreadnought battleships and cruisers, hulks that were never meant to move without their own power. They rig massive hawsers to the damaged bows and spread the load across whatever structure still has strength. Heavy chain bridles are dropped to form a deep catenary, turning the tow line itself into a shock absorber against the sea. The towing vessels must maintain a precise, agonizingly slow speed. If the tugs pull too fast, the hydrodynamic drag of the ocean will crush the temporary forward bulkheads on the salvaged ships. If they move too slowly, the massive steel tow line goes slack in the water. When the next ocean swell catches the dead ironclad, the slack line violently snaps taut, creating a lethal, jerking force that can shatter the towing gear or rip the deck cleats clean off the hull. The entire transit is an exercise in extreme mechanical anxiety, governed entirely by the unforgiving physics of mass and momentum. A skeleton crew rides each unpowered hulk across the swells, living in a constant, listening vigilance. With dead boilers, they have no real pumps, no lights, and no heat, only lanterns, hand tools, and the sound of timber and steel complaining under load. If a patch starts to open, they do not fight the sea with machinery. They fight it with their hands. Slowly, methodically, the towing fleet conquers the distance. They pull the massive, crippled beasts out of the shallow straits and across the sea. The meticulous harbor patching and the calculated rigging of the towing hawsers hold true against the ocean swells. In a monumental feat of operational logistics, 6 major warships survive the perilous transit. The heavy pre-dreadnought battleships and armored cruisers finally arrive at the Japanese naval shipyards, safely delivering thousands of tons of captured steel. The surface fleet has successfully relocated the massive prizes to their sovereign dry docks. The external structural patches have held and the hulls are secured. The immediate threat of sinking is resolved, but the true cost of the harbor siege is hidden deep inside the engineering spaces. The ships survive the tow, but their internal organs have been fatally poisoned by the very ocean they now sail on. Not a single operational boiler remains inside the prizes. The tow has delivered the hulls to Japanese yards, but when the watertight doors swing open, the machinery spaces are dead. Pitted tubes, seized valves, and fittings eaten down to the metal. The bombardment and the mud did damage, but saltwater galvanic corrosion finishes the job, turning flooded engine rooms into an unregulated battery that strips the less noble steel away. Japanese engineers condemn the original steam plants outright. Lighting them would mean rupture and a lethal steam blast. So the dockyards cut access from above, rig chains, and lift the ruined boilers out, leaving the ships hollowed to their ribs. Then the rebuild begins. New, Japanese-made Miyabara water tube boilers are lowered into the emptied spaces, seated on fresh foundations, and tied into new runs of high-pressure steam piping. The new plants feed the surviving main engines, while machinists realign shafts and couplings until the geometry is true again. Month after month, the yards hammer, cut, and rivet until these captured battleships and cruisers steam out under Japanese-built power. The successful resurrection of the captured Russian fleet definitively shifts the balance of naval power, proving the monumental strategic value of aggressive wartime salvage.